All right, today we're going to tackle two huge ideas in math that, honestly, help run our entire world: relations and functions. We're going to go on a little journey, starting from a tangled mess of connections and ending up in a world of perfect, predictable order. I mean, just think about it for a second. Everything is connected to something else, right? People to their jobs, students to their grades, cities to their GPS coordinates. It can feel like total chaos. But what if I told you that math gives us a system to describe and organize any connection you can possibly imagine? Well, that's exactly what we're about to dive into. So, the first tool we're going to pull out of our mathematical toolbox is something called a relation. And it sounds kind of formal, but it's our absolute starting point for mapping out how things link together. At its heart, a relation is nothing to be scared of. It's really just a list of pairs that shows who is connected to what. You take an item from one group, you pair it with an item from another group, and that's it. That's a connection. Okay, now for the slightly more official definition. You'll hear that a relation is a subset of the Cartesian product. That sounds super complicated, right? But all it really means is this. The Cartesian product is just the giant pool of every single possible connection you could ever make between two groups of things. Let's make this real. Imagine you have set A with A, B, and C in it, and set B has 1, 2, and 3. The Cartesian product is just us listing out every single possible pair-up: A, 1, A, 2, A, 3, then B, 1, B, 2, and so on. It's the universe of all possible connections. But here's the key. A specific relation, let's call it R, isn't that entire universe of possibilities. Nope. It's a specific selection we make from that pool. In this case, we've decided our relation only includes 3 connections. This is our very first step in creating order out of all that chaos. Okay, so now that we can define connections, things get really interesting. You start to see that different relations have their own personalities. They follow certain rules that give them special properties. Let's look at 3 of the big ones. First up, we have reflexive. This is a simple but really powerful idea. A relation is reflexive if everything in the group is related to itself. Just think about the phrase, is the same height as. Well, of course, you're the same height as yourself, right? That connection, you, always exists. Next, we've got symmetric. This just means the connection is a two-way street. If A is related to B, then B has to be related to A. The classic example here is a sibling of. If my sister is my sibling, then you better believe I am her sibling. The connection is totally mutual. So you see here, a symmetric relation is a partnership. If the pair 1, 2 is on our list, its reverse, 2, 1, has to be there too. But, a ton of connections are one-way streets. Think about is the parent of. If I'm the parent of my child is definitely not the parent of me. And finally, there's transitive. This one is all about chain reactions. If A is connected to B, and that same B is connected to C, a transitive relation guarantees that A gets to skip the middleman and connect directly to C. Think about is less than. If 3 is less than 5, and we know 5 is less than 10, then it's a sure thing that 3 is also less than 10. So, relations are pretty cool. They can describe almost any kind of connection. But what happens when almost isn't good enough? What happens when we need our connections to be totally reliable, totally predictable, every single time? Well, that brings us to a very special, much more disciplined kind of relation. And that is the million-dollar question. Because for so many systems in our world, we can't have any ambiguity. We have to know that if we put one thing in, we will get one and only one specific thing out. That absolute need for predictability is what gives birth to the idea of a function. Just take a look at this real-world example: student exam grades. Adam gets an A, Dila gets a C, Ahmad gets a B. The most important thing to notice here is that every single student has exactly one grade assigned to them. Adam can't have both an A and a C for the same exam. That would be chaos. This simple, strict rule is the very essence of a function. And this leads us right to the formal definition. A function is simply a relation that follows one extra crucial rule. Every single element in your starting set, the domain, has to be paired with exactly one element in the ending set, the codomain. Not 0, not 2. Always 1. The best way to think about this is that a relation is kind of like a social free-for-all. One person might have lots of connections or maybe none at all. It's messy. But a function is a vending machine. You press one button, that's your input, and you get exactly one soda. That's your output. every single time. It's predictable, it's reliable. So, this strict rule of exactly one output gives functions some pretty amazing abilities, or as I like to call them, superpowers. And these properties let us classify functions and understand what they can do on a much, much deeper level. There are three main types. First, you've got injective, or one-to-one. This is where every output is unique. Think of it like social security numbers. No two people share the same one. Then you have surjective, which means every possible output in the second set actually gets used. And finally, you get bijective, which is the holy grail. It's both of them combined, a perfect pairing. A bijective function is basically a perfect matchmaker. Every input has its own unique output, and every single possible output is claimed by an input. There are no leftovers on either side. It is a flawless, perfect one-to-one correspondence between the two groups. And this perfect pairing unlocks the ultimate superpower. Because that mapping is so perfect, so unambiguous, it means you can run the whole thing backwards. A bijective function is invertible. So if your original function maps a to y, b to x, and c to z, its perfect pairing means we can just reverse all the arrows. The inverse function will take y and give you a right back. It'll take x and lead you back to b. You can always get back to exactly where you started. And that really is the entire journey. We started with this messy, chaotic idea of connections, and we gave them some structure with relations. But then, by adding just one simple rule, the vending machine rule, we transformed them into the predictable, powerful, and even reversible world of functions. So this leaves us with a final thought. Our modern world, from the software on your phone to the GPS that gets you home, is absolutely built on the backs of functions. So the next time you use a piece of tech, just ask yourself, where's the function here? What's the predictable one-to-one rule that's making this whole complex system work so flawlessly? It's something to think about.